This horn holds exactly pi cubic units, even though its surface has infinite area. Fill it from the wide end, and the total amount poured approaches one perfectly ordinary number. Now try to coat its inner wall, and the area you need to cover never stops growing. Same object, finite inside, infinite skin. And yes, that sounds like the volume ought to run out at exactly the same moment as the surface. It doesn't. Here is the shape. Start with the curve y equals 1 over x, beginning at x equals 1. Spin the region underneath it around the x-axis. The result is a horn that gets narrower forever. It never reaches a sharp endpoint. It simply keeps going, with a radius that creeps closer and closer to 0. Watch what happens when we cap the horn at increasing lengths. At length 2, it looks like a stubby funnel. At 10, it has a long tail. At 100, the tail is almost too thin to see. At 1 million, the picture barely changes near the tip, though mathematically, the horn still has nearly a million units left to travel. Now fill each version. The amount rises quickly, then settles toward pi. 3.1, 3.14, 3.1415. It is visibly running out of room, but unwrap the corresponding surface into a strip and the strip keeps extending, slowly, stubbornly, forever. That split is the whole mystery. How can a tail add almost no space while continuing to add unlimited skin? The answer is hiding in how radius controls those two measurements, and one tiny difference gets amplified all the way to infinity. The tail gets away with this because volume and surface area respond differently to a shrinking radius. Take one very thin slice of the horn. Its radius is 1 over x, and its thickness is a tiny amount called dx. For volume, that slice behaves like a thin disk. The face of the disk has area pi times radius squared, so the slice contributes roughly pi times 1 over x squared, times dx. The square is doing enormous work here. Move 10 times farther down the horn and the radius becomes 10 times smaller, while the disk area becomes 100 times smaller. Surface area sees a different piece. It cares about the rim of that disk sweeping along the horn. The rim has circumference 2 pi times the radius. Only 1 power of the radius appears. Move 10 times farther out and this contribution shrinks by a factor of 10. That is much slower. There is also a small correction because the wall slopes. A slanted strip is slightly longer than its horizontal shadow. For this curve, that correction is the square root of 1 plus 1 over x to the fourth. Far down the tail, it becomes extremely close to 1. It matters for the exact formula, though it cannot rescue the surface from what is coming, so the competition has reduced to 2 decay rates. The inside accumulates pieces shaped like 1 over x squared. The skin accumulates pieces behaving almost like 1 over x. They both approach 0. That fact alone tells us almost nothing. Infinitely many tiny contributions can still build a finite total or wander upward forever. And this is the turn I love. The entire impossible horn is really a contest between those two innocent-looking tails. 1 over x squared settles. 1 over x refuses. 1 over x squared settles because each new stretch of horn contributes dramatically less volume than the stretch before it. We can see that without trusting an integral yet. Divide the tail into doubling blocks. First x runs from 1 to 2, then 2 to 4, 4 to 8, 8 to 16. Every block is twice as long as the previous one, which sounds dangerous. But throughout each block, the radius has roughly halved, so its cross-sectional area has dropped to roughly a quarter. Twice the length times 1/4 the area gives about half as much volume. Each successive block contributes at most a fixed fraction of the one before it. That produces the familiar geometric pile. Something, then about half as much, then a quarter, then an eighth. Infinitely many blocks, finite sum. The horn keeps gaining length, while its remaining capacity collapses towards 0. Now the exact calculation. Add all the thin disks from x equals 1 to some cutoff L. The volume is the integral of pi over x squared. Its antiderivative is negative pi over x, so the result is pi times 1 minus 1 over L. Let L head to infinity. 1 over L vanishes, leaving pi. That formula lets us test the absurd scale directly. Cut the horn at 1 million units. The volume already captured is pi times 1 minus 1 millionth. The entire infinitely long remainder holds only pi millionths of a cubic unit. All of infinity, from there onward, squeezed into less volume than a tiny speck on this scale. Okay, that part is gorgeous. Length keeps marching forever, while capacity has effectively finished. Yet we still haven't accounted for the skin. If doubling blocks tame the volume so cleanly, what happens when we apply exactly the same test to the surface? The same doubling test turns against us on the surface. Take the band from x equals 1 to 2, then 2 to 4, then 4 to 8. The blocks double in length. Their typical circumference falls by about half because circumference follows the radius directly. Double the length, halve the circumference, and the product stays roughly constant. So every doubling block adds another substantial patch of surface. The bands get thinner, yes, but they also get longer. Those effects cancel closely enough that the horn pays almost the same surface area bill again and again. One block, another block, another. There is no shrinking geometric pile this time. The exact surface formula includes the slant correction we saw earlier, 2 pi times the integral of 1 over x, multiplied by the square root of 1 plus 1 over x to the fourth. We do not even need to evaluate that monster. The square root is always at least 1. Therefore, the horn's surface is at least as large as the integral of 2 pi over x. And that integral is 2 pi times the natural logarithm of L. Logarithms grow painfully slowly. They still grow without a ceiling. To double the accumulated benchmark, you may need to extend the horn by a ridiculous factor, which is why a drawing can conceal the divergence so well. At L equals 10, the logarithmic estimate is about 14.5 square units. At 1000, about 43.4. At 1 million, about 86.8. Keep replacing L with 10 times L and the estimate gains the same amount again. The growth never ends. There it is. The volume blocks diminish by half. The surface blocks keep charging roughly the same amount. The radius was squared in one calculation and left to the first power in the other, and that single exponent decides which infinity wins. There is a whole family, and the dividing line is wonderfully sharp. Replace the radius 1 over x with 1 over x to the power p. Turning p changes how aggressively the horn narrows. Volume squares the radius, so its tail behaves like 1 over x to the power 2p. Surface area, apart from a slant factor that becomes harmless far out, behaves like 1 over x to the power p. The standard rule says the integral of 1 over x to the power q converges exactly when q exceeds 1. For volume, q equals 2p, so finite volume requires p greater than 1/2. For surface, q equals p, so finite surface requires p greater than 1. That leaves an entire interval where the split occurs, p greater than 1/2 and at most 1. At p equals 3/4, the volume sees exponent 3/2 and settles. The surface sees exponent 3/4 and diverges. At p equals 1, Gabriel's horn, the volume sees exponent 2 and settles, while the surface hits the logarithmic border and diverges. Push p beyond 1, say to 2, and both measurements become finite. Draw p to 1/2, and even the volume diverges. The distant tail has become too fat. Watch the parameter line. At 1/2, volume crosses from infinite to finite. At 1, surface does the same. Between those thresholds, the strange creatures live. This is what gets me. Finite volume with infinite area is not balanced on one miraculous formula. It occupies a whole region of possibilities. Gabriel's horn is simply the cleanest border case, with its endless surface announced by the harmonic integral. And now we can ask what this says about shape more broadly, because everyday intuition quietly assumes that length, area, and volume must scale together. Our intuition failed because ordinary objects end. A mug, a bottle, a trumpet, each has a final wall and a smallest manufactured detail. For those shapes, shrinking the interior usually drags the boundary with it. An infinite tail can separate them. The same separation appears one dimension lower. A curve can have infinite length while enclosing finite area. Add ever finer zigzags to a boundary. Their total length may grow without limit, while the enclosed region stays inside a small box. Gabriel's horn lifts that mismatch into 3 dimensions: finite volume, infinite area, boundary. The recipe is clear. Build infinitely many pieces. Make each piece's volume shrink fast enough for the total to converge. Let its boundary contribution shrink too slowly, or stay roughly constant across scale blocks. Infinity does not supply endless capacity. The rate of decay decides everything. Return to the horn at 1 million units. Its remaining volume is pi millions, almost nothing. Its remaining surface area is still infinite. Cutting away practically all remaining capacity fails to impose even a finite upper bound on the remaining skin. On the full horn, the liquid gauge stops at pi. The unwrapped surface keeps going. Every cross-section pays radius squared into volume and radius into area. Squaring the shrinking radius makes the interior contribution summable. Leaving it unsquared keeps the boundary contributions on the harmonic edge, a tiny exponent difference. One extra copy of the radius, enough to put the inside and skin on opposite sides of infinity. And the horn from the opening still has no endpoint. It never needed one. Its capacity finishes anyway.